Hello, hello, hello. There is the two-dimensional Vicky. Good morning, good morning. There is the two-dimensional representation of Anita. Good morning, good morning, and there is the textual communication of Vicky and Jean. Good morning, Jean. All right, we are rocking and rolling. Hold on. There are more people. Good morning, Vanita. Or did I say that? Yes. Oh, so we got a double avatar and verbal expression from Vanita. We got animated avatar and verbal expression from Vicky. We've got a verbal expression from Jean. Good morning. Good morning. Awesome. And I see, and we've got a avatar, or at least not a black box from Miriam. Good morning. And an avatar from Jocelyn. Good morning. Oh, good. Thank you in a private chat from somebody. Thank you. I'm good. Thank you. I know I'm looking more different every day, but yes, good. Thank you. Who else did I not? Amelia, good morning. Good morning. Um, okay, we're gonna start. So here we are. So I will admit, actually, so I apologize. Well, I'll put it in the chat I'll put it in the chat right now. Hang on one second. I probably should have put it in Google Classroom. Um, Hold on. I'm going to put something in the chat. One second. Good morning. I know someone's in the waiting room. Sorry. Um, I know someone's in the waiting room. I'm just okay. Oh, more people, more people. Okay, okay. Okay. So yes, I just put in the chat and I'll put in again as more people come in. I do not have your exams yet. I apologize. I mean, there are a lot that things are a lot right now. They're very important to me. You will get them. Um, I I'll notify you as soon as I have them, but until I have them, I won't have them. That doesn't make it. Anyway, please just bear with me. I appreciate your patience. Good morning. Good morning. So we're just going to keep proceeding until I have them to get back to you. Um, um, but a couple of things legit. Good morning. Yes, a couple legit. So we're going to get back to material now. But so obviously, so last week was another sort of intense week. I didn't see you much. Well, anyway, things are getting a little bit intense on my side sometimes. Um, which leads me to say this. What I noticed, I didn't even realize that the work done by a constant force assignment was just already scheduled automatically in Google Classroom. Like I got ahead of myself with that, I guess, at the beginning of the semester. I didn't even realize that that had been already assigned to you this quickly. And many of you awesomely, responsibly made an attempt at that assignment, even though we haven't talked about that stuff at all. Amazing, totally impressive. What I'm here to just say is basically we're at the point now where a lot of you are in many respects ahead of me, both in the sense that you've taken your exam, which you were supposed to do, and I now the ball's in my court with the exam. And also, many of you have now done a couple of really hard homeworks without getting much feedback or instruction from me, the Newton's Law homework and the work by a constant force homework. Impressive. You are ahead of me, in other words, or you are definitely not behind. The ball is in my court now, and I am falling a little bit behind, as you can tell. So just logistically, what that means. First of all, sort of an apology. I didn't the work done by a constant force homework was sort of assigned automatically, and I didn't even realize it. I wouldn't have done that if I had been more mindful. I would have given you more time or said more things about it before I signed it. So with that one, if you everybody can still get all the points on it, believe me. But if you already did it, you've already gotten 20 out of the 24 points just for doing it, which is amazing. Um, and you'll either get feedback or the other 4 points. That's, just remind me, but if you care about the other 4 points, but amazing if you've already done it. I'm talking again about homework 9, which was sort of assigned prematurely and accidentally by me. Um, Similarly with homework 8, you automatically got 51 out of the 65 points just for doing it on time. And the rest of the point, either you're going to get feedback from me or you're going to get the rest of the points. You could gently remind me in like a week or so. Uh, um, right now, the priority is the exams on my end. So what I'm trying to say is, first of all, we're not going to have new homeworks for a while. Possibly, we might like have one more before the final exam, but now it's time for me to catch up with you and also for you guys to breathe out and catch up in the little time between, like Thanksgiving and the final and all of that. So what I'm trying to say is don't worry about new big assignments coming down the pike. Whatever you're still trying to revise from old assignments or in the last two, if you haven't done them yet, it's totally understandable because they sort of did cascade on you. Um, we're going to all just try to catch up with the material. I'm going to try to catch up with instruction, and you try to catch up with whatever you still want to turn in. I hope I'm being clear. Basically, I'm saying you guys are good. You're the ball's mostly in my court now for a while. So you worry about tying up loose ends or patching holes that exist on your side and believe that you still can. I mean, try like old things or gaps that need to be closed absolutely can still be closed. I'm being too euphemistic, but I think you understand what I'm saying. And if you don't, let me know. What I want to do now is get back to the topic and the material of Newton's laws. But because I was out Wednesday, and because again, I'm repeating, I'll put in the chat again since more people have come in. Hold on a second. Let me just put in the chat. Um, like, excuse me. Wednesday, you had Professor Lou. I know in my head what I think I want to keep addressing with regard to Newton's laws and forces and all that material, but it would actually help me help you better if we could take a couple of minutes first casually for me to find out from you where you are. So here's my questions. First of all, what are you up to in lab right now? Like what is what is the very next thing that is due for you in lab? If any way that you could tell me, I mean, chat, voice, you'll get points for responding, but I'd love to know what's your very next thing that's due in lab? Is that a challenging question? Wait. Oh, wait, you can hear me, right? Hold on. Hello. Wait. Okay. 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 That's fair. Oh, that's why it's a confusing question. Okay. Thank you, Vicky, and thank you, Annie. Oh, okay. Now we're talking. Okay. Yes. Maybe I should have phrased the question differently. Okay. You don't have anything due this week. That's good. Okay. So maybe breathing out in general. Good. We have another class for data collection. Okay. Thank you, Annie. Thank you, Vicky. For lab 5. So that's the slow down lab. Oh, the up. Okay. With the up. Okay. Okay. Very helpful. That's what I want to know. All right. All right. So this is good. That's actually perfect. That means you're in the topic that I was hoping. That's a hard lab, by the way. I mean, it's a fat to me. It is one of my favorite labs ultimately, but it's hard while you're doing it for sure. It's a lot, and especially if you haven't talked a lot about all of those issues, including friction, in a class. For sure, it's hard. So I'm glad that you have another class for data collection. I'm glad you don't have anything due right away. Hopefully, I can sort of I'm going to try to catch you up to the material to make all that easier for next week. That's good. That is helpful. So let me ask you another question then. with what did you talk at all, either with Professor Liu on Wednesday? Did you actually talk, did any instructor in any way talk with you guys about diagrams, specifically either system schemas or free body diagrams? And I know they're expected in the lab. So you probably have had to, and I know they're referred to in the homeworks, but have you actually gotten any instructional communication about system schemas or free body diagrams from either professor? And this is not a, I'm just literally asking factually. You did. Wait, you did FBDs and system. Okay, one person, and you could be honest. I noticed some people in the direct chat are being maybe more. You could be honest, and you could do in direct chat if you. I'm not asking. This is not maligning, professor, or like. I literally just want to know where you are, so I know how to help you. Honestly, um, so some people are saying in the public chat you diagrammed, you did FBDs and system schemas, which I believe, but okay, and then some people are saying yeah, but some people are saying need more practice in the direct chat, which is totally fair and totally believable. Um, but like, okay, so I'm gonna be even more. Wait, need more practice. Even people. Okay, actually, to be honest, it's really helpful that now. Okay, that's super helpful. That's because I would think that I would think that you would, and that's sort of what I'm prepared to try to help with because I think they're really important and they usually are really confusing and blah 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 blah. To actually hear the people who are saying that you did do them, but even they admit that they need more practice is like really helpful. I mean that sort of implies to me that we could that no one will be bored or frustrated if I give you more. So good, fine. Wait. Okay. Okay. This is kind of what I wanted to know. Like good. Really. Okay, I'm over. No, I appreciate the honesty because it is my instinct. It would be my assumption that this would be useful, but I would hate to do it if like everybody was like, no, no, we've done it a million times. Please, can we move on? Like, okay, so fine. Good. Um, okay, I'm gonna do that in a second then. I'm gonna try instead of like walking through the individual homework, well, I might do some, but I'm going to try to get as quickly as I can to what you need to know about this stuff, like for your lab and everything, because I know it's been moving fast. So bear with me. I got a couple more questions just to figure out how to do this. Okay. But yes, I would think this would be, and someone else is here. Blah, 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 blah. Um, so super quickly, when you were with two more questions then. When you were with Professor Liu on Wednesday, what was it about? What could someone just quickly tell me in the chat or something? Like basically, what did you all focus on with Professor Liu? Was it homework 7 or was it the lab or was it diagrams or was it friction? Um, or was it all over the place? That was with Professor Liu. You went over the 3 laws of Newton with Professor Liu. Oh, okay. So she didn't get into wait. Some problems, okay, but like, is it fair to say that it wasn't a major, diagrams were not a major focus of Wednesday? Is that a fair inference on my part? Like with Professor Liu on Wednesday, diagrams were not a major focus. Is that fair? Yes, fair inference. Okay, thank you. I love it. Okay. I always forget. By the way, I'm so sorry. Whenever I ask these questions, I forget, of course, it takes people time to type their answers. Like I really need to take that into account. So yes, okay, okay. They should have those 3 dots things that they do on iMessages where they anyway. Okay, which is creepy, but so is the way I look. Okay, okay. Thank you. Thank you. Okay. I mean direct chat person, thank you. Okay. So I think I know what I'm about to do. And all right, and for no. I actually got it. I got it. Thank you. No, but both I think are okay, thank you. That's very nice. Um, okay. So I think I know what I'm gonna do. Yeah. All right. And bear with me. What I'm going to try to do right now, I'm going to try to do this whole diagram thing so that you understand. I'm sort of borrowing from okay. Yeah. I guess I'll start it from a problem in the homework Yeah. Yeah. All right. I'm gonna switch screens. I'm going to base and we'll see how far we get today. I bear with me. I'm going to try to walk through my way of like how all this works, how Newton's second law with all the diagrams and the forces and everything works in general. As of my starting focus, I'm going to use a problem from your homework assignment, but I'm going to try to then expand it into all the lab implications. Okay, so you'll be, and I'll let you know when I'm like expanding it. But so what I'm trying to do is sort of quick, segue from the homework to your lab to cover as much as like so. So what I'm saying is this here. Okay, so bear with me, and I may not wait. Today's Monday, so this may continue into Wednesday again. You won't have any new, if by somehow, if I'm missing, if some new homework pops up in Google Classroom, I don't think this is, but if some new thing pops up in Google Classroom that's like a completely new material, someone just alert me and text me like it's a mistake. Okay. What we're trying to do for the next few days or many days is all get all of this material clear with ourselves. Okay. I promise. So, like, whatever I'm about to start right now, even if I don't finish it today, I'll continue Wednesday, and you don't have to worry about new things landing on your plate. I have to worry about getting things off my plate back to you. Okay. I hope that's clear. And just bear with me. Again, the exams, they're going to take a while. Like they always take me a little while anyway, but it is a little harder right now than usual. So just bear with me. I apologize, but they're not forgotten. I promise. Okay. So the screen share that what's on the screen right here, this is from your second most recent homework. Apple sitting on the table, blah, blah, blah. So I'm going to use, so unless you stop me, if you say in the chat, no, this is exactly the one that Professor Lou spent all the time on, and we're totally bored of this. If you tell me that, I will switch gears. But I think this one, if I talk about it, I can then turn this into your lab situation, even if it takes 2 days. Okay. I.e., I can add friction, which I think you need to hear about as well. So is this good? This one that's right here, multi-force warm-ups. Can I just get a show of hands? Can I walk through this with all the pictures and the diagrams and then add layers to it to turn it into the lab? Does that work for people? Show of hands, electronic hands. Thank you, Andy. Okay, thank you, Vicky. Okay, that's good. I'm worried about Vincent and Gabriel. Are they ambivalent or are they okay? Well, if there's a better idea, I'm not being just because I haven't seen you in a while. I just want to make this work. If there's a better idea, put it in the chat. I'm serious, but okay. I'm going once, going twice. All right, so I'm going to switch screens back to the Apple. Okay, I'm switching screens. Okay, so all right. Okay, now I'm switching screens again. Pardon me. Okay. Right. So hopefully, again, let me know if you don't know where I am or whatever. All right. So we've got an apple on the table. All right. That's my picture. Right. But then it asks system schema. Okay. Here's the point of it. And this is very important. Well, let me back up for a second. The ultimate, and you might want to write this down. The ultimate thing that's going on with all of these problems, all these force problems, the ultimate thing is F net equals MA. The ultimate purpose of all of this is that we're ultimately trying to figure out the A of some M. Like really. In fact, the first 2 months of this course were all about analyzing the A of some M. All of what we've been doing up until now, like everything on the midterm, weirdly or not, is all really about understanding what it means to say that an object has an acceleration at a point in space at a point in time. Like really, like all of the stuff we've been doing up until now has been like the power and meaning of acceleration. And the whole idea has been that that once you know the acceleration of something at a point in space, at a point in time, then you can predict where it's going to be at some future moment or where it was at some past moment if you're solving crimes. Like, really, really, like, bear with me for a second. What we're really doing in physics is we're always trying to predict where something is going to be when or where it was when, right? And what we realize at the beginning of physics is that velocity is like a step toward that, but the real step is acceleration. And the business, everything we were doing up until now, it's like all of the implications and details of how acceleration is related to velocity, but it's not the same thing. And then all the vector stuff is like how you deal with acceleration in like 2 dimensions or 3 dimensions. And all the calculus stuff is like what it means that acceleration could be true at like a moment, right? Like as opposed to an average. So everything was all about if you know acceleration, here's how you can predict like x equals 1/2 at squared, blah, blah, blah. Okay. Now what we're saying is, but how do you know the acceleration of something? Like all of that stuff that we were doing was studying effects of kinematics. Now we're saying, what's the cause? We're saying, like, where did something get an acceleration from? How do we even know it's acceleration in the first place? And the answer is Newton's second law. The analysis that we're doing from here on in physics is saying if you know all of the forces acting on an object, on a mass, if you know all the forces acting all in the different directions of three-dimensional space, then if you put them together in the right way, if you add them all up in the vector way, then you will know the acceleration of that object at that moment. And then once you know the acceleration of the object, you go back to all the old physics stuff that we've just been learning. Honestly. This is like my big picture view. So the deal is it's all about F net equals MA now. It really is all about the second, mathematically, it's all about the second law now. But the difficulty, the challenge, the reason I'm now going to like hopefully address what like thankfully Vincent and Annie and direct chat people are saying is like the issue is wait a second. Fine, add up all the forces and you can get the acceleration. We get that. But like exactly like how do you add up all the forces? How do you know which forces are acting at all or which ones are acting how or which ones are acting in what direction and how do you add them all up? How do you get the what I'm trying to say is this is all about everything I'm about to do is all about this law, like at the bottom of the thing. But really what it's about is figuring out how to expand, unpack, substitute in the left side. All the diagrams I'm about to talk about, anything, if I start getting abstract or sounding abstract, the focus is trying to identify all the F's, the forces that we're going to add together on the left-hand side so that ultimately we have something we can divide by M to get A. That is the purpose. And it is just hard enough that we have different stages of diagramming to get us there. And we use the first law and the third law to understand what counts as a force and what doesn't and where to put the forces. But it's all about identifying the forces and adding them together to get the left side of Newton's second law down there. Okay. So that said, here's our picture of an apple on a table. The first thing it asks us for is a system schema. A system schema. The purpose of a system schema is to identify every force acting on the mass, whatever in this case, the apple. Okay, the apple is the mass. So first we do a system schema, literally so that we can find out what forces are acting on this apple or whatever our mass is and what forces are not, right? Because all we ultimately want to plug into F net equals MA is the forces that are acting on some M. So first we draw a system schema to find out what the forces are at all. In other words, identify every force acting on M as a physical interaction. And note, since you've probably already seen this, like direction and magnitude don't matter yet. They don't matter at all in this kind of diagram. Don't matter. So what we do, so tell me, so I'm going to turn the page. So we draw. We first always draw a dotted circle to represent the M that we're talking about. The M, the mass, the object of concern, the object of focus. Like every one of these problems is focusing on a particular M. Again, it's all about finding out what the A of that M is. So the first thing you do in a system schema is you draw a dotted circle representing the M. It's a circle because you're trying to emphasize this is an actual object. Like this apple is like an actual physical material thing, right? Then what you do, and I'm just talking now because I don't want to. No, I'll try. All right. So first of all, dotted. I guess I am going to write it down just in case. So always, these are the rules. What I'm writing down now is the rules for a system schema, and the. Sorry, I'm getting myself all. There are rules for drawing a particular diagram, but I want to emphasize this diagram is not like just an exercisey thing that teachers put students through, like to keep them busy. This is like the way, it's a calculational tool. It's not a rough sketch. If you follow the rules of this diagram and then you use this diagram to make the next diagram and you follow those rules strictly, then the whole idea of this procedure is that it locks down exactly what the left side of F net equals MA will be so that you can then do the math. I'm going to say this one more time and then move on. But part of why you've been practicing the 5-step method like all along in physics is to get in the habit of realizing that the math is not the hard part of physics. And you all kind of know this already. The hard part is setting up the math. That's the physics of physics, is set, right? And what we're really trying to get you used to, especially now, is the way to properly set up math for physics is usually through very carefully obedient diagram tools, whether they're graphs or vectors, or in this case now, schemas and free body diagrams. If you follow the rules of diagramming strictly, the diagrams do the work for you, and you don't have to think. Like, you don't have to think like creatively. They just do the work for you and set up the math that then you do. So the rules are you do a dotted circle for M. This is always, these are the rules, like SS rules, system schema rules, okay? Then, sorry. Okay, then now here's the key. Again, for every single object in the world, in the universe, that is interacting with your M, any and every object in the world that is interacting with your M, you're going to draw a solid object, a solid circle representing that object. Now, there's two key aspects to this. First of all, interacting means, and so this is where Newton's third law comes in. Okay, third law is like trying to remind us what. So we're trying to draw. We're trying to identify forces, right? But the first thing we're saying to ourselves is a force doesn't just come from. It's not a Star Wars thing. Forces don't just appear out of nowhere, and they don't just like exist inside of objects. We think Newton's third law, a force is an interaction between two objects. So if our goal is to identify every force acting on this mass, then the only way to know what forces are acting on this mass is to think of other masses, literally other material, physical objects in the world that are somehow pushing or pulling on this mass. There's not a force unless there's another object somewhere. So, what are those forces? Well, I'll tell you, and then I'm going to tell you how I know. First of all, there's a table underneath this object. There's a table. Something in the chat. I'm almost excited because it. Good. Okay. That's very good. I see the direct chat. That's yes. I'm not. That's a fancy. Good. That's a fancy word for something, and I don't know the fancy word yet. I mean, I ultimately agree with you, direct. And there's only one person in the direct chat, so yes, very good. I'm not going to use that word just yet but I'm getting to that. Yes, very good. You're ahead of me. That's all. What I want to think now, in other words, in the system schema, I literally just want to name other objects that are interacting with this object. Now, how do I know if another object is pushing or pulling on it? The first thing I just ask myself is anything else touching this object at all? If something is touching it, it is definitely pushing or pulling it. And with one exception, good. Okay, now we're to. Okay, wait. Okay, wait. This is awesome. All right. You know what? I see a lot of things happening in the direct chat, and they're all great. So, okay, hold on. Let me back up for a second. I agree with what you guys are saying. Here's what is it on a table or a desk? Do we say table? Okay. Okay. First thing is to answer what I think is happening in the chat is, and I will say what the fancy words were that. So there's a lot of okay. The two objects that I think are interacting with the mass are the table and the entire Earth. Where did and clearly many of you knew that I was going to do that, and that's great. What the word that I'm not using yet, the word that was in the chat that I'm not using yet is the normal force. Okay, I'm not saying that word is wrong. I love that, but it's a very confusing word until we're used to it. And more to the point is, I don't think it belongs yet in this diagram. I think it belongs in the next diagram, and I'll tell you why. Right now, I'm not looking for anything abstract. I'm looking for things very concrete. I'm looking to say, okay, the first thing, what I'm trying to say right now is if there's a force, then there's two objects interacting with each other, which specifically means two objects pushing or pulling each other, which specifically means if ever, no matter how complicated something gets, even the lab problem, if you're looking at an object and you want to know what forces are acting on this object, for every force that you believe is acting on that object, there's got to be another object in the world making that force happen. Like, and so conversely, if you really have no idea, if you're like, I don't know what the forces are, you ask yourself first with the system schema. You don't get fancy. Now, we don't get fancy yet. We just say, what's out there affecting this object? And the way you know, here's the thing that people don't realize, it's simpler than it sounds. The only other way, the only way that an object, number one, can push or pull object number two is if either it touches it or it's planet Earth. Like literally. Like the thing is, for there to be a force, in mechanics, in this level of physics that we're in right now, for there to be a force, there literally has to be touching, with the one exception, the one huge exception of what we call planet Earth. Now, that's such an exception, it's such a big exception that it's like really important to talk about, and it confuses everybody if you don't remember that it's an exception. So let's get this straight. Anytime I ask myself for the system schema, I'm just trying to identify ultimately the number of forces that are acting. So what I do every time in a system schema is I ask myself, what are all the objects that are touching? And any single object that are touching my object, my M, I identify each one of those. And then plus I say, okay, and there's always planet Earth. So you could even put entire Earth. You could call planet Earth, you can call it entire Earth. They both, whatever. And many of us, yes, get used to the fact that for some reason that we don't know yet, we've just noticed in life, the entire Earth below us seems to be able to pull on anything and everything toward it all the time without touching. It's very mysterious. We're very used to it. It's been happening for thousands of years, and for millions of years, and it happens every day. So we all very used to it. So it's true that the Earth is always there in every single system schema. Entire Earth is always there, and it's always pulling with this force that we ultimately call gravity, right? But that doesn't mean we know yet what it is, exactly what it is or why. Sorry. But yes, it's always there. So fine, in every single system schema, I draw one solid circle that represents the entire Earth. I do that, yes. Then every single other object that's touching my mass at all, I draw a solid circle for that. In this case, there's only one other. It's called the table. The object is the table. So I just write down, oh, sorry. Oh, good. Oh, okay. Apparently this is helping at least one person. Okay, good. And I know I'm talking too good. So I'll keep going though. So I'm saying every single system schema, yes, draw the entire Earth first. It's always there. I agree. I'm not trying to make a small thing of it, but it's a big thing. It's always there. You could draw it first. But please understand that the reason we always draw it first and we make a big thing is because it's a mysterious exception. Earth is the one and only thing ever in all of what we're going to do for the rest of this course. Earth is the only thing that can pull or push without touching. Anything else you ever identify, there has to be a touch in order to put in the system schema. So now I'm going to go, and I know there's still other words in the chat that I haven't addressed yet. I will in a minute, but I'm going to go a little further now. So far, in this case, we've got two objects that are affecting the M. We've got table and we've got planet Earth. And I'm intentionally just calling them by their proper names because I'm trying to emphasize that forces are not magic. They are interactions between actual real material objects. In this case, an Earth and a table are each interacting with the mass. So now I go to the next rule. So that was like 2A and B. The next rule is draw lines. Okay, now this is where hopefully even those of you who are bored and thinking you know all this already, this is where I'm now getting into a realm that perhaps will help you with the lab and perhaps you haven't thought of yet. Wait, okay. Now, what I'm going to say is in the system schema, and of course, I hope you understand everything I'm saying is the rules in general. Like all of this are rules. They would apply no matter how complicated the example is. I'm just starting with this seemingly simple example. So now we're going to take those objects and we're going to connect them to the mass with lines. And the purpose of this is that each line that we draw, we're going to be very careful about these lines. They're just lines. They seem all simple and everything. And literally, they're line segments. They're not arrows. They're line segments. But the whole purpose of what we're doing now is that every single line that appears in the system schema is literally going to become a vector in the free body diagram. And every vector in the free body diagram is what we account for in the math on the left side of F net equals MA. So we're building, like we're trying to create a situation where as long as we follow rules, we'll know exactly what to plug into the left side of F net equals MA, even when it's really complicated, like it is in the lab. Okay, so what we're going to try to do now is lay down these lines. And once we commit to these lines, they're going to carry through the rest of the diagrams. So there's a rule for these lines. The basic rule is one touch equals one line. So for example, with the table is, well, actually, even that, even that's a little bit, but actually the table, let's say the table's actually already complicated. Let's say that in this case, someone was pulling the apple with a string, which they're not right now, but just as an example, say someone was pulling this apple with a string, and that so the string would also be an object in the picture. Then we would connect that string solid circle to the mass with one line because the string is touching the mass once. So we would get one line, and that would be a force that would then go into our free body diagram. Okay. In fact, you know what? I'm going to add one more. Hold on one second. I see how I'm going to do this. Except to rough. Just add this word right here. Rough. Okay. And I'm even going to say, even the table, because apparently in this problem right now, as it stands right now, it doesn't ever say that the table is rough or that the apple is moving or anything like that, right? Okay. I'm going to assume, I'm going to assume um well, I'll get to that in a second. Okay. So first of all, if there's one touch, generally speaking, like a string or something, a one-dimensional kind of pull, if there's one touch, then there's one line that you draw. End of story. That's the rule. But there's two big exceptions to the rule. And the truth of the matter, as you can already see because of the way I'm stuttering and everything, there's two exceptions to that rule. Only two, exactly two exceptions to that rule, but they tend to come up in every single diagram. So let's be careful about them. The first exception, so the rule, what's the rule? The rule is one touch means one line. But here's the two exceptions. Exception one is gravity is not a touch, but it's still a force. It should still get a line. So the first exception is in every single diagram that you have entire Earth, you connect the entire Earth to your mass with one line every single time. You could start, in other words, every single system schema, if you're following me, and you probably already got in this habit, you can always just start by drawing your mass in a dotted circle, your entire Earth in a solid circle, and you can connect the two with a solid line every single time. I mean, it's always there. Earth is this universal exception. And by the way, this power of Earth to do this thing called gravity, kept physicists from Aristotle through Galileo, through Newton, through Einstein mystified. It was always the thing that mystified physicists. It's always everywhere. We're used to it, but it does seem to not, until they finally worked it out, it doesn't seem to behave like other things. So it's not, I'm not trying to confuse you. But anyway, Earth gets one line, even though it doesn't have any other touch. Excuse me, even though it doesn't have any touch. That's exception one. The other exception, this is where now things start getting to the lab and things get complicated. The other exception to the one touch, one line rule is whenever you have two rough surfaces pressing together, okay? If you have two surfaces that are rough, that are pressing together, the truth of the matter is, and that could be the case right here in our situation, which is why I'm like stuttering around a little bit. Like the problem really didn't specify if the apple was rough. It didn't really specify if the table was smooth or not. If there's any roughness to this table, and realistically, unless specified, there almost always is in life. If the table is at all rough, if the apple is at all rough, then the bottom surface of the apple is pressing down on the top surface of the table. And similarly, by Newton's third law, the top of the table is pressing up on the apple. You got two rough surfaces pressing against each other. Whenever you have that, the reality is, if surfaces are rough, if you like stared, if you zoomed in and looked at them really closely, you would see that they're like made of like bumps and valleys, like they're like little like nooks and crannies. They're like English muffins or something, like if you look at them close enough, right? And so when you press two rough surfaces together like this, realistically, it also makes them hard to rub against each other like that, right? So in other words, when things press against each other perpendicularly, they also end up pressing against each other parallelly. When they press against each other perpendicular to the plane of contact, they also rub against each other parallel to the plane of contact. Automatically, a force in one axis seems to generate or motivate a force along a perpendicular axis when surfaces are rough and when they press against each other. Now, again, I'm not saying all forces do this. If you have a string or like a fishing line and you pull up on a fish, none of that happens. You can pull things by touching them and none of that weirdness occurs. You can even push things with a finger and none of that weirdness occurs. But when you have a surface that's rough pushing against another surface, then the one touch between the two actually generates two perpendicular force components. So in general, if you have one surface pressing on another and you don't know any other facts against them, you would draw two lines connecting them. Okay, that's the safest thing to do. We might not end up using one of the lines if it turns out that one of the surfaces is not at all. Okay, great question in the chat. So what it's called that I'm talking about, and I will, of course, write this down and be more specific in a minute, but what I'm talking about is the friction force and the normal force. And to be clear and fair, like someone else in the chat already brought up one of those words before, and I sort of blew it off, or I postponed it for a minute. I'm intentionally not writing this down yet, these words, because what I think is that they really belong in the free body diagram and they belong a little bit later in the analysis. Right now, I'm trying to focus our attention. But yes, what I'm talking about right now is I'm saying when rough So I'm talking literally here. What I'm literally saying right now is that when two surfaces push against each other, when two surfaces push against each other, that force that is called normal force. Let's get it straight. The word no, but it's a horrible word because you could see why. Normal in math, and please, this is like the hard bit right here that I'm on right now. So I'm glad people are paying attention. And please, anything you can write down would be really helpful. Normal, the word normal in mathematics just means perpendicular, like literally means perpendicular. So what I'm saying right now is when two rough surfaces press against each other, I'm saying surfaces, like two-dimensional regions of matter, not lines, not strings, not hands, surfaces pushing against each other. And when they're pushing against, not pulling, I'm not talking about magnets. When two rough surfaces push against each other, you can imagine a plane of contact between them. Like two surfaces are like two pieces of bread. And if it's like a turkey sandwich, like the turkey in between the bread is what I'm calling the plane of contact. The Euclidean like plane to like that they're both pressing up against. So whichever way that plane is, when they push perpendicular to that plane, we call that the normal force. And the push that results parallel to the plane, the rubbing, sliding, we call the frictional force. So I'll say it one more time. Normal is like the pressing. And it doesn't like it doesn't, it could be horizontal, it could be vertical, it could be angled. It's just the pressing against one surface against another. That's what normal means. And friction is the rubbing, sliding. They're both part of the same phenomenon. They're two axes, two components of the same phenomenon. The overall phenomenon does not have a name. The overall phenomenon is literally surfaces pressing against each other. You could call it pressure, I suppose. But and so go back to we'll get into the details of that, like in the free body diagram and in the math and in your lab and all that. But right now, what I'm just saying is, okay, from here on in, when you're just trying to figure out what forces are acting, you just got to ask yourself first, what things are touching the object plus planet Earth? And you have to be aware that if something is touching the object in a surface pressing kind of way, then there might well be two implications of that, a pressing and a rubbing. I keep saying might because if the surfaces are smooth enough, if it's like maybe is even the case here, if it's a smooth apple on like a polished table and they're so smooth that no one's even worrying about friction, then maybe one of these lines is eventually going to be irrelevant and go away. But if you don't know, and especially in the lab, like from the start, I'm saying so I'm going to move on, but I'm saying when you draw a system schema, gravity gets a line, surfaces pushing against each other, especially if they're rough, get two lines, and every other object that's at all, like if someone were now pulling this also with a hand, or there was also something else, every other object in the system schema would get a line. Every touch gets a line, with the two exceptions, gravity and surfaces pushing. And now I move on because now I've done my system schema. Notice, here's my system schema right at the top there, right? It's very simple. It's so simple that it seems like it didn't do anything. It seems like a lot of talk for no reason, but it isn't. Because now because now I can go to the free body diagram and start generating arrows based on these lines. Every single one of these lines is going to be an arrow. And in fact, Okay, now I'm going to go make a free body diagram. I'm going to turn every one of those lines into an arrow. And the arrow is ultimately going to help me know about direction and magnitude. Please notice, last thing, notice all the work I'm doing here is just to figure out what are the darn forces. Because that is the hard part. Like you guys were I mean, there's more hard parts to come, but like you guys were sort of implying in the chat, like even knowing what are the forces or what is the force is hard. So the first thing with all my chatter, I'm trying to emphasize just whatever in the world is interacting with your object is generating a force. How do you know if it's interacting with your object, if it's pushing or pulling it? How do you know if it's pushing or pulling it, if it's touching it, or if it's planet Earth? Like that's what it comes down to. It's all about touches plus planet Earth. So now I've identified them as regular everyday objects in this diagram. It's like an Earth and it's a table. Now I go to the free body diagram. And I'm going to go first to what we call a pure free body diagram. So first of all, every line in the SS becomes a vector arrow in the FPD. Okay. The M now becomes a point. All vector arrows emanate from the point. That is, each arrow starts with its tail at the point and is drawn out from the point. Um, all other objects are now gone. Um, second line gone if okay. So now we're going to turn each one of those lines, we're going to turn it into an arrow. And it's going to be an arrow, so there's not going to be anything on the other side of the arrow anymore. Like we identified those objects to figure out where the lines are. Now we got the lines. That's what our goal was. So now we're gonna get rid of those other objects, and we're just going to focus on our mass and just have arrows coming out of our mass. That sounds weird. And so the other objects are now gone. And now one last thing. And now we start using the fancy names. I guess so I'll show you what I mean. So here we go. So our object of focus, our mass, is now a point. Here's our M, right? It's just a point. And each one of those lines we're going to bring in now and turn it into an arrow. So like we had a line that was connecting this to Earth before, right? Well, now I'm going to focus on what is the Earth actually doing to it. My first focus was, is the Earth doing anything at all? Now my focus is, what is the Earth doing to it? And what the Earth does, what the entire Earth does to an object in every single case is it pulls it down, as you all know, right? So I'm going to draw an arrow pointing down. Okay. Um, Wait, I'm looking at the chat. Okay. So the Earth is pulling down on the. Now, I'm not going to call that arrow entire Earth anymore. Well, I'll go on, but okay. So I draw the Earth pulling down. Now, what's another object? Another object is the table. The table is underneath the apple and it's pushing up on the apple. How do I know it's pushing up on the, well, first of all, how do I know it's pushing? Because push means away and pull means toward. The table is not a magnet, right? And everything is either a push or a pull. So if you're not pulling something toward you, you're pushing something away from you. The table is not a magnet, it's pushing the object away. And more specifically, if the table weren't there, we know the apple would fall down. So the table is stopping the apple from falling down. The table is pushing up. So the table gets an arrow that points up. Let me just straighten this out. So the table is pushing the object up. Now, I could write table on that upper arrow, and I could write, wait, let me go. Hold on, one more thing. Also, we've now decided I do. There's one more line in our diagram, right? And that was to protect us just in case friction was going to play a big role here. But it sounds like from the problem, it doesn't ever say, it doesn't ever give us a coefficient of friction. It doesn't tell us how rough the apple is or how rough the table is. It doesn't sound like friction's playing any role in the problem. So that second line that I drew to be careful, that I drew to protect myself, that I always do, if surfaces are pushing, I don't have to carry that over into the diagram because that second line in the double line thing ultimately was going to represent the phenomenon of friction, like Annie and direct chat person were asking about. And it doesn't seem like friction's playing any role in this problem. So I did drop that second line. Okay. So every other line from my system scheme has been accounted for. As an arrow here, I've got arrows. Now I want to, and they're starting to look like vectors now, like they have direction and magnitude. So I'm going to start being able to do math soon, but I need names for them. I'm not going to call them table or planet Earth anymore because now I don't care anymore. I don't care what these other objects are. Like, I don't want to confuse myself. The only object, the only mass now of concern is the apple. And things are happening to the apple. So now I'm just going to make up, once and for all, I'm going to make up names for these actual forces, these interactions that came from the other objects. As I think you know, this force right here becomes called mg. I think you know this. Let me quick, and it's always true that okay. Little sidebar here. I'm sure you've heard, a little confusing. I'm sure you've heard it. I know there's 10 minutes left. How much do I want to get into this? Weight is not the same thing as mass. And you should definitely, you either overly know this or you underly know this, but weight is not the same thing as mass, right? Mass is M, it's measured in kilograms. Weight means literally the downward pull of planet Earth. Weight, the word weight literally means gravitational force. So weight is a force. Mass is a resistance to a force, right? Mass is measured in kilograms. Weight, like all forces, is measured in newtons. A newton is a kilogram times a meter per second squared. So whenever from now on so that arrow, that downward arrow in this diagram is the weight of the object, the pull of Earth on the object. That pull is m times g, because F net equals ma, right? To say it as fast as I can, if you think about it, if our whole situation was just an apple falling to the ground, if the only force remember, what's the definition of free fall? Free fall is when the only influence acting on an object is gravity, is planet Earth. So if an object were falling to the ground and the only force on it were weight, then weight would equal ma for that object. And you know that when something is in free fall, its a is g, right? Like, you know, when things are in free fall, their acceleration is that g number, 9.8 meters per second squared. So the force that's pulling something to the ground is not 9.8 meters per second squared. It's mass times 9.8 meter per second squared. I'm saying that in a way too much for some of you and too quickly for some of you. But what I'm saying is the force of gravity from now on in every one of these diagrams is mass times the acceleration due to gravity, mg, right? So that goes in that line that was the entire Earth is now a downward arrow called mg. Now, I'm looking at the chat. Good. You could call it, okay. Wait, okay. One direct chat question. You could call it F sub G. You could call it that. Yes. You could call it force sub gravity. Perfectly fine. And I would never take off for that if it were like in an exam or something. But the why it's sort of a good habit to follow other physicists and call it mg is that once you start plugging into the math, like once you use all this information to expand the equations and solve for things, the mg is highlighting that to get the number for it, you literally could plug in the number of kilograms and multiply by 9.8, and you would literally have the number of newtons that is the force. So it's getting you a jump start on the math to call it mg. But yes, if you called it F sub gi, that's correct. And weight is a vector. Yes, Annie, and others. What we're now, and I know I'm running out of time, we'll continue this Wednesday, but yes, what I'm trying to do now is the system schema was not a vector diagram. It was on purpose just an identification diagram, just to what is a force and what's not. Then we pull the lines out of the system schema and we turn them into vectors now. And yes, weight is a force. Every single force is a vector. It has magnitude and direction. Like, yes. So weight is a vector. And if this mg, again, I know some things are confusing and some things are not. I'd rather talk about whatever is confusing to you guys. So like, if this is confusing enough people, let me dwell on it even more on Wednesday. So I don't know if that answers the questions or not, but yeah, so mg is there. And I guess so that we can have some closure. What I'm saying now is that this upward force, okay, this now circles back to something someone said in a direct chat like 20 minutes ago, very honorably. Like, I'm now going to say that this upward force is the normal force. And I draw n like in that funny way with serifs so that I'm distinguishing it from the n for newtons. I'm saying this is my free body diagram now, but let me be very careful about this. So like someone asked a while ago, are we talking about normal force here? Yes. Now I'm talking about the normal force. But what that normal force is, that upward arrow, that is simply the pressing of the table against the surface of the apple. That's what I mean by normal. I mean that there is a surface pressing against another surface. The surface of the table is pressing up, pushing up on the bottom surface of the apple. So we call that normal force. Like, really, that is the normal force from the table acting on the apple. And like, why I'm struggling to make this is a subtle point, but like why I didn't want the normal force in the other diagram, but I wanted here is, first of all, I don't want you guys to think, even though it's called normal, it doesn't mean that it is normally in every single diagram. There are a lot of situations where there's no normal force. Let me repeat that. There are a lot of situations where there's no normal force at all. It is not a rule that there has to. Okay, good question. You are really paying attention. Direct. Yes, I can. Great question, direct chat person. So someone in the direct chat said, what would be an example of no normal force, which is a perfect question. So first of all, free fall. If something's just falling, there's no normal force at all. And that's not obvious. I'll give you another example in a second, but even that is not obvious. People think all the time that there is. If something is just in free fall, the only force in the diagram is just mg. And what that tells you is just because there's mg, let me back up for a second. There's always mg. There's no exception to that. There's always, every single object has weight. So that's why in the system schema, the first thing you draw is the entire Earth if you want. And the first arrow you draw in a free body diagram is mg. That will never get you wrong, or like that will never be wrong. There's always gravity. But just because there's gravity doesn't mean there's a normal force. And a lot of people tend, especially if we do these diagrams out of order or something, people think that the normal force is something that normally comes along to counteract gravity. Totally not true. If something is in free fall, there's no normal force at all. Let me give you another example because it's such a great question. And then tell me if it makes sense. And I know we only have 3 minutes left. Another example is I could be pulling on something could have like this apple, like I could be pulling a fish out of the lake, like I'm fishing. So I have a fishing line, and the line hooks into a fish, and I pull the fish out of the lake. Like that's a real situation, right? The fish would have weight, so there would be mg pulling down on the fish for sure. Then there's this rope, this line pulling up on the fish for sure. There would be 2 arrows in the diagram for a fish. But oh, great. Okay, cool. Thank you, direct chat person. But neither of them would be normal force. Like if you're pulling on something with a string, there's no normal force at all. There's something called a tension force, which like does things that are different from the normal force. And really, as long as people are asking about it, because this is one of the biggest misconceptions in physics, like, and this is why I'm like struggling so hard. And of course, it comes up in the lab. Like to cut to the chase, by the way, is there a normal force in the lab? Oh, yes, there is a normal force in the lab. And I'll get to that Wednesday, hopefully. But a couple of and why do we care so much about when there's a normal force and when there isn't? We care about the normal force so much because the normal force is what allows us to analyze and predict the friction if there is friction. There's never friction without a normal force. There must be a normal force if there is friction. If we know the magnitude of the normal force, we'll know the magnitude of the friction, all that you need for the lab. But, for example, in the lab, everything is on an inclined plane in the lab. So the normal force is up on an angle, right? So we have to get to angles and everything. But the thing I'm trying to say right now is people have this idea that the normal force just automatically counteracts gravity because it's called normal. So it sounds like that. And because it is in a lot of pictures, but it's not the case. The normal force does not automatically counteract gravity. It could be off at a weird angle, even when gravity isn't, for example. So wait, so I know as usual, I'm saying a lot and I'm not saying anything. But I know it's 12:05. So I'll pick up exactly where we are on Wednesday. You don't have new homework, just catch up where you are in the homework. I'll still accept things happily. I'll pick up on this and I'll try to relate it to the lab Wednesday. Bear with me, but the questions are great. Keep the questions coming. And even if this takes me, I mean, they're very helpful. So, wait. Oh, no. You will learn the last question in the chat. You will learn about the tension force even in this class. You will. But I just don't want you to think that the tension force, and yes, the tension force is very important in 204. You're right. But what I want to make clear is the tension force is different in that tension, when there's tension, that has nothing to do with friction. Normal goes with friction. So that's why we have to focus so hard on the normal force. Just don't think that normal means normal. It doesn't mean always there. It just means perpendicular. That's what normal means. But okay, these are great questions. I'm going to shut down just because I'm going to shut down the recording. We'll just keep going.